What is moment of inertia? Hello guys and girls, welcome to lessonsforcivil.com. This lesson is about a very important topic in civil engineering, moment of inertia. But before starting this lesson, if it is the first time you're watching us on YouTube, don't forget to subscribe the channel, and then you will get automatically noticed of every last video we upload. Okay, now let's start. We show the amount of moment of inertia with a capital I, but what does it mean? Well, in simple words, the moment of inertia is a property of cross-section that defines how strong the beam is going to act under pure bending moment. Consider a beam like this that has a very thin cross-section. These thin cross-sections are too weak and they can tolerate a little amount of bending moment. And that is why they can easily bend and we cannot put a large amount of bending moment on them. For this reason, we never use such a beam in our steel structures. Instead, we usually use I-shaped beams, C-channels, and boxes because they are more strong against bending moment. Here is the point. The thing that makes a big difference between thin cross-sections and other cross-sections is the moment of inertia. Now let's see how can we calculate the amount of moment of inertia. Okay, to calculate its amount, we have to take two main steps. Before calculating the amount of moment of inertia, we need to know where the neutral axis is. Please look at here. If I apply a positive bending moment while the upper part of the cross-section is under compression, the lower part experiences tension. In other words, alongside the height of the beam, pressure turns to tension. So definitely we have somewhere in the middle of the area that has zero stress. This area is actually a line called neutral axis. For many simple cross-sections, it's very easy to find the location of the neutral axis. For symmetrical cross-sections such as boxes like this, it is exactly at the middle. But for unsymmetrical cross-sections, we have to do some calculations. This video is actually not about how to find the location of neutral axis, and in another lesson I will explain it in depth. For now, we assume that the location of neutral zone is given. Okay, for any given beam, we can consider a coordinate system of x, y, z like this. Here I assume that y-axis is alongside the beam. So Ixx represents the moment of inertia around x-axis. And it is equal to the integral from 0 to whatever the y value is, y squared dA. This is the general formula that works for every complex cross-section. But fortunately, in civil engineering, the cross-sections are usually simple, such as a C-channel or an I-beam, which is a combination of several rectangles. So in most cases, you don't need to work with this equation. Instead, this table gives the amount of moment of inertia for typical cross-sections. For rectangle cross-sections, for example, it is equal to b cubic h divided by 12. In this equation, b is the width and h is the height of the beam. But what about more complex cross-sections? Here is a strategy to calculate the amount of moment of inertia for some cross-sections that consist of a combination of typical geometries. For example, to calculate the amount of I for this I-shaped beam, we have to take three steps. First, we need to find out where the neutral axis is. As I said before, if the cross-section is symmetrical, it is exactly at the middle. In the second step, we try to divide the cross-section into simpler parts, such as rectangles, triangles, or circles. For each one, we identify the location of neutral zone. And using the table I gave you, you can calculate the amount of moment of inertia for each part. Finally, to find the overall moment of inertia, you can use this formula to add them together. The main reason we use this equation is that there is a distance between local neutral axis and the overall neutral axis. Okay, here is an example. As you can see, the dimensions have been given and we have to calculate the amount of moment of inertia around x-axis. The first idea you may have is to use the original formula for moment of inertia method, which is a complicated integral. But actually it's not a good idea, because as you can see, an I-shaped beam consists of 3 rectangles. So it would be a good idea to use the simplified formula to calculate the amount of moment of inertia for each rectangle. As you can see, the amount of moment of inertia for rectangles is equal to b cubic h divided by 12. And after that, we can use another formula to calculate the overall amount of moment of inertia for the cross section. In the following formula, I is the amount of moment of inertia for each rectangle, A is the area of the rectangles, and D is the distance between local neutral axis for each rectangle and the overall neutral axis. So the first step is to identify the location of neutral axis for each rectangles and for the I-shaped beam. Fortunately, all the rectangles and even the I-shaped beam are symmetrical geometries. So the location of neutral axis is exactly at the middle. As you can see in this picture, I have calculated the amount of D between each local neutral axis and the overall neutral axis. Okay, let's start. Okay, first of all, I want to rewrite the equations I need. The moment of inertia for a rectangle is equal to b cubic h divided by 12. And the overall amount of moment of inertia can be calculated according to this formula. As you can see in this formula, di is the distance between local neutral zone for each rectangle and the overall. Now if you put the amount of dimensions into the equations, you can easily find the amount of moment of inertia for this I-shaped beam. Okay, now there is one important question to ask. What is the unit of moment of inertia? As you can see, the dimensions has been given in millimeter, but during the solution, I put them in meter. So the unit of this number would be M4. Okay, this lesson is over. If you find this video useful, please don't forget to like and share it with your friends. Practice as much as you can, and if you have any question, you can leave it in the comments below. Until the next lesson, goodbye.